In a physics laboratory experiment, a 0.51 kilogram cart rolls forward at a speed of 3.2 meters per second until it collides with another cart. The second cart is 0.73 kilograms and is stationary before the impact. After the impact, the first cart is recoiled, going backwards at a speed of 1.1 meters per second. Any friction on the carts is small enough that it can be ignored. What is the velocity of the second cart after the collision, and what type of collision is this? This problem will focus on using skills of conservation of momentum, collisions, and what types of collisions there are, and more generally using vectors and the importance of direction. Let's start with a sketch of the situation. I'm going to draw it both before and after the collision. So initially we have cart 1 coming in, going forwards, and cart 2 is stationary, so its velocity is 0. After the collision, we're told that cart 1 has recoiled and is now going in the other direction, and we don't know what cart 2 is doing. That's what the question is asking us, is to find the velocity of cart 2 after the collision. Because we're told that any friction on the carts is small enough that it can be ignored in this last sentence, this tells us that momentum is conserved. That means that the initial momentum of the system of two carts is the same as the final momentum of the system of two carts. That's because there are no external forces on this system. So remember, we know that if the external forces on a system are equal to 0, the outside forces, then the momentum that the system starts with, that initial momentum, is going to be equal to the final momentum of the system. Don't get confused and think that this depends on what type of forces are involved, or that the total force has to be 0. There's a lot of force involved, right? These carts hit together, that's a big force. But because we're considering both carts part of our system, those are internal forces. The external forces from things like friction on the track on the carts is small enough that it can be ignored. That's the external forces that we're talking about. So now let's look at this equation for conservation of momentum. Here's the equation that comes out of conservation of momentum. Let's break this down and look at each term. This first term here, m1 v1 initial, is the initial momentum of cart 1, that 0.51 kilogram cart that's moving. This term is the initial momentum of cart 2. So this is cart 2's momentum before the collision. And hopefully you can tell that this is going to cancel out. This is just going to be 0 because the initial velocity of cart 2 is 0. We're told that it's stationary before impact. Then on the other side of the equal sign, we have the final momentum of cart 1 after the collision and the final momentum of cart 2 after the collision. So let's go ahead and plug in the numbers that were given. We know mass 1, and we know that initial velocity, that 3.2 meters per second. And then we have mass 1 again. And here's where we need to be careful and remember that we're dealing with vectors. Why these vector arrows are so important is that we are told that cart 1 after the collision is going backwards at a speed of 1.1 meters per second. If we consider going forwards at 3.2, if we're saying forwards is a positive speed, then going backwards is going to be negative. So I need to make sure that I make this negative 1.1. Then we know mass 2 is that 0.73. And finally, there's that V2F, that velocity that we're trying to solve for. So we now have enough that we can solve for V2F. And we get that V2F is equal to 2.45 meters per second. And because that comes out as a positive number, that tells us that the cart 2 is moving forwards, which should hopefully be what you would expect and what you would picture just based on your own experience, that if cart 1 recoils and goes backwards, cart 2 is going to be going forwards. Now let's consider that second question. What type of collision is this? There are 3 types of collisions: perfectly inelastic, partially inelastic, and elastic. Let's talk about each one in turn. A perfectly inelastic collision means that when the 2 objects collide, they stick together after the collision. That is not what happens in our problem. One cart goes forwards, the other goes backwards. So we know that it is not a perfectly inelastic collision. Now let's consider the other 2. What's the difference between a partially inelastic collision and an elastic collision? If you're just looking at the collision, you can't necessarily tell which this is. What's important is the special thing that we know about elastic collisions. What we know about elastic collisions is that not only is momentum conserved, but kinetic energy is conserved. We don't lose any energy when the 2 objects collide. In other words, when the 2 objects collide, the force between them can be treated as a basically conservative force. As we'll recall from talking about energy, that energy is conserved as long as there are no non-conservative forces doing work. So it's almost like if this is an elastic collision with these carts here, that would mean that there were 2 springs on the carts that kind of pushed on each other, since a spring force is an elastic force, is a conservative force. And so we're not losing any energy there. It's sort of an idealized situation. So how can we determine then if we have a partially inelastic collision, which means, hey, we lost some energy, but they didn't stick together, or we have an elastic collision where not only was momentum conserved, but we also had kinetic energy conserved. We had no energy lost. How do we tell which is correct? We can evaluate the kinetic energy beforehand and compare it to the kinetic energy afterwards and see if we've lost any kinetic energy. Here are our terms for the kinetic energy both before and after the collision. We know that we're considering the kinetic energy of the whole system. We're not ever claiming that the kinetic energy of just one of the objects doesn't change. We're trying to look at the kinetic energy of both cart 1 and cart 2 before and after the collisions. You'll notice that cart 2's initial kinetic energy is 0, just like its initial momentum is 0, because it's initially stationary. Kinetic energy depends on speed. If the speed is 0, the kinetic energy is 0. So if we plug in our values here, we get that we start with an initial kinetic energy of 2.61 joules. If we plug in all our numbers here, including that answer that we got for the velocity of the second cart, we get that our kinetic energy after the collision is 2.21 joules. So in other words, we've lost 0.4 joules of kinetic energy. This tells us, since there was a loss of kinetic energy, that this is not an elastic collision. This must be a partially inelastic collision. Since we had a loss in kinetic energy of 0.4 joules, this means that our collision is partially inelastic. This tells us, by calling it that we have lost kinetic energy even though we haven't lost any momentum in the system. And that means that the force between those carts, that internal force as cart 1 hits cart 2, is not a completely conservative force. That means that there's some friction or something else we can conceive of as a non-conservative force there.